All right, let's take a look at this one real quickly. Sodium emits light with a wavelength of 330 nanometers when an electron moves from a 4p orbital to a 3s orbital. What is the energy difference in the orbitals in kilojoules per mole? This is a question people try to answer using Balmer or something like that. Well, first of all, it's a sodium atom, so you can't use the Balmer equation for it because you only have the Balmer constant for hydrogen. Also, Balmer is basically just energy levels. Here you're moving between S and P's, and there are very slight energy differences between those when you're looking at different subshells. Fortunately, you don't need any sort of equation. This is really a sheep in wolf's clothing instead of a wolf in sheep's clothing. You've been given a wavelength, and they want energy. This is kind of like one of the ones you started off doing the chapter. You're going to go from wavelength to frequency using the speed of light equation. Then you're going to go from frequency to energy using Planck's equation. So it's kind of the same song and dance we've been doing all along. So let's go ahead and get the dance started. Solve for frequency. Well, we know our value of C, 2.998 times 10 to the 8 meters. We're going to have to do a quick unit conversion for our wavelength because they give us nanometers. But at this point, you probably have done so many nanometers to meters conversions that you have already done the math in your head. Or if you are not, you haven't, then I haven't given you guys enough homework. So now we plug in 2.998 times 10 to the 8 meters divided by 3.30 times 10 to the negative 7th meters gives us a frequency of calculator fingers today, people. 9.08 48 times 10 to the 14th hertz. And I have my units wrong. I'm asleep at the wheel here. Speed of light's in meters per second, obviously, so that we can get to our hertz. Now I have my frequency. So I'm going to go up here and use my Planck's formula. And this is where paying attention to your units is really helpful. They want kilojoules per mole, right? Planck's formula, when we write it as E equals Planck's constant times frequency, refers to only one photon. We're wanting to refer to a mole of photons. So how many should we use? How many photons should we use? 6.022 times 10 to the 23rd photons. So let's take a look. Let me clean things up just a little bit here. So we have E equals our number of photons times Planck's constant times frequency. So we've got energy equal to a mole's worth of photons, 6.22 times 10 to the 23rd, times Planck's constant, 6.626 times 10 to the negative 34th joules second times our frequency, and I didn't give myself enough room. And we're using that frequency from last time. Computers are great until they're not. And let me grab my eraser here. All right, I'm recording live here. So let me see if I can't get rid of that little. Here, we'll get rid of this way. All right. So I plug all this into my calculator and I get a value here. And we're going to have one more cutesy step after all this is done. Now this gives me joules per mole because this is photons in 1 mole, right? So this gives me units of joules per mole. They want kilojoules per mole, so I still have one more cutesy finishing step. 10 to the third joules in 1 kilojoule. So I get 362.5. Oh, well, 362.5 kilojoules per mole. Or if we wanted scientific notation, 3.62 times 10 to the second kilojoules per mole. You say potato, I say potato. That's it. Beep.